We would like to continue our exploration of double integrals, and we would like to look at the case where the domain of definition is the domain of integration, I should say, of a given integral is not so friendly to Cartesian coordinates. So for example, we saw that if we have an integral over the unit disk, then when we write it as an iterated integral, the endpoints are going to involve square roots, which eventually might lead us to pretty complicated computations. Not necessarily impossible, but pretty complicated. And here's where the main idea comes in. The unit disk, as I said, has a very simple description in terms of polar coordinates. Let us recall that when we talk about polar coordinates, the polar coordinates of a given point are two numbers, r and theta. R is the distance from the origin, and theta is the angle between the radial segment connecting the point to the origin and the positive x-axis. So the domain D in polar coordinates can be described, the unit disk in other words, as r comma theta, so the pairs of all numbers r and theta that represent the polar coordinates of points, so that r is between 0 and 1, and theta is between 0 and 2 pi. And here, there are a few remarks that we should make regarding the specific choice of inequality symbols. In particular, let's take a look at this one first. One might think that by writing theta to be less than or equal to 2 pi, some points are considered twice. In fact, it's true that if a point has polar angle 0, then the same point can be taken to have polar angle 2 pi. In other words, the polar angle of a point is not unique. You can have, each point has infinitely many possibilities for its polar angle, but sometimes we restrict the polar angle within a given range, very often 0 to 2 pi or negative pi to pi. But in any case, it seems that some points are taken twice. However, this is integration, this is computation of volumes, and if you consider the part which is considered twice, then that's a segment, and whatever lies above it doesn't have any volume, so it doesn't add anything to our computation. In fact, we could have equally written 0 less than theta, less than 2 pi, and again, nothing would have changed. The other thing that we might want to look at a little bit carefully is the point 0. The point 0 is a very special point when it comes down to polar coordinates, because its polar angle can be taken to be everything and nothing. I mean, it's an angle between a degenerate line segment and the x-axis. And it could be, sometimes it is quite common to exclude it from considerations with polar coordinates, but in our case, in general, it will not alter or complicate our computations. So with this in mind, we see that the domain of integration in polar coordinates becomes a rectangle. And so if we proceed in a slightly naive way, we might say, well, if we have an integral, a double integral of a function over the disk, then we might as well turn into polar coordinates and so express x and y in terms of polar coordinates. Let me here recall that x is equal to r cosine theta, y is equal to r sine theta. And the other very interesting relation that we need to remember here is that x squared plus y squared is equal to r squared. This is really the Pythagorean theorem. And these are the transition formulas back and forth between polar coordinates and Cartesian coordinates. So you might think that we can consider this integral and in fact go from 0 to 1. That would be the range for r. And 0 to 2 pi, that would be the range for theta. And it should be a very, very smooth computation. But if we look at the corresponding iterated integral in Cartesian coordinates, then we will realize that, or we should realize that the very definition of the double integral was based on those boxes that we were creating and the volumes of those boxes are equal to the height, which is the value of the function at a given point within that little rectangle, times the area of the base. And in our case, the area of the base, so if you have a rectangle with dimension delta x and delta y, then the area is delta x times delta y. So here, if we try to do the same thing in polar coordinates, so we would have these small quote-unquote polar rectangles, like this one, for example. And let's draw a larger version of it so that we can see it right here. So something like this, where this is your delta r and this is delta theta. Then you could ask, is it true that the area of this is delta r times delta theta? Or actually, I could even relax this a little and say almost equal to that. And the answer is no. And one of the ways that we can see that this is not true is, unlike the case of Cartesian coordinates, where if you take a polar rectangle with the same dimensions anywhere in the space, then its area will be the same. That would not be true for polar coordinates. Meaning, consider the following case. So here's one polar rectangle, which has a given delta r and a given delta theta. And then here's another polar rectangle that has exactly the same delta r and the same delta theta, but exactly because it's much further away from the origin, it seems that its area is much larger than the area of the other one. And we can understand that if we go even further, then that area will become even larger. So this relation would simply be not true. What is true, however, is that the area is approximately equal to not just delta r times delta theta, but r times delta r times delta theta. It's not equal to that. It's equal to that plus something else that eventually literally vaporizes as we consider smaller and smaller, or the sum of all these things really vaporize as we consider smaller and smaller partitions, or finer and finer partitions into smaller and smaller rectangles. So we can see that there is this magical factor here that somehow should appear inside our integral. And this factor is what we're going to refer to as a correction factor or a distortion factor. But there's a much better name, which is based on the name of the French mathematician Jacobi, and it's called the Jacobian. So if we wanted to summarize the process of computing an integral in polar coordinates, then we would recognize that we have three distinct steps. So step one is to take care of the domain. So this would be step one. Step one is to express the domain in polar coordinates. Step two would be, so step one is the domain. Step two is to express the integrand, the function to be integrated in terms of polar coordinates. This is done by just replacing x by r cosine theta, y by r sine theta, and possibly use the fact that x squared plus y squared is equal to r squared. And step three is to insert the Jacobian as an extra factor in our integrand, the function to be integrated. So these are the three steps, and it might be a good idea to actually proceed with an example in order to see how this works. So as our first example, let's compute the double integral d of x dA, where d is the part of the unit disk that lies in the first quadrant. So if we wish to compute this, then it's a good idea to try to see first of all what the domain looks like. So the domain D here is, as we said, the part of the unit disk that lies in the first quadrant. And in terms of polar coordinates, this is simply all pairs of coordinates r comma theta, where r is between 0 and 1, and theta is between 0 and pi over 2. So if we take our integral, then in our first step, and exactly because it's a rectangle, it doesn't really matter in what order we perform the integration, we're going to go from 0 to 1 in terms of r, and 0 and pi over 2 in terms of theta. So that accomplishes step one. For step two, we have to express x in terms of polar coordinates, and that is done by replacing it with r cosine theta. So that's step two. And step three is to insert the Jacobian. And we can see now that the integral that we obtain is actually of that type that, as we discussed before, it splits, meaning that the endpoints of integration are all constant, which implies that integration is taking place over a rectangle. And also the integrand itself is a product of two quantities, one that contains only r and another that contains only theta. So we can easily rewrite this integral as the product of the integral from 0 to 1 r squared dr times the integral from 0 to pi over 2 of cosine theta d theta. And this integral here is going to be r cubed over 3 from 0 to 1, which is equal to 1/3. And this integral here will be sine theta from 0 to pi over 2, which is easily seen to be equal to 1. So the value of our integral is 1. And that completes our computation. Let's go to another example. This time, since you've seen already an example, you might want to give it a try to see how you would do it without the help of the recording. So let D be the region between the circles with radii 1 and 2 centered at the origin, for which x is less than 0 and y is less than 0. Compute the double integral over d of xy dA. As you can see in many of these examples, the integrand seems to be the simplest possible. I mean, you know, some polynomial in two variables, but this doesn't make the task of computing the integral exactly trivial. In fact, one needs to really process the domain and also proceed with the integrand in terms of polar coordinates. But let's see how this is done. And first of all, let's try to understand what this domain looks like. So we have our two circles, the one with radius 1 and the other with radius 2. And it says to focus on the part between the two circles that for which x is less than 0 and y is less than 0. So these are domain D right here. And D, in terms of polar coordinates, can be given as all r's and thetas, such that r is between 1 and 2, and theta is between pi and 3 pi over 2. With this information, we should be able to transform our integral into an integral in polar coordinates. So let's see. So we take our integral. And we go from 1 to 2 with respect to r, and then from pi to 3 pi over 2 with respect to theta. Now, x is r, so that accomplishes the first step. Then we have r cosine theta. R sine theta is the integrand, so that gives us the second step. And of course, the integrand has to be complemented by inserting the Jacobian, which is r, and that's the third step. And we're now ready to go. And again, we obtain an integral which can be split. So how do we do that? Well, we have, with respect to r, we have the integral from 1 to 2 of how many r's do we have? We have 3, so that will give us r cubed dr. And with respect to theta, we have the integral from pi to 3 pi over 2 of cosine theta, sine theta, d theta. And let's compute them. So the first one is r to the 4 over 4 from 1 to 2. And this is a simple computation. On the top, we will have 2 to the 4th, which is 16 minus 1 to the 4th which is 1. So 16 minus 1 is 15 divided by 4. On the bottom, things are a little more interesting. We should do a substitution. So you can take u to be sine theta. You could also take it to be cosine theta. It doesn't really matter. Du will be cosine theta d theta. And what do we get when we integrate? So cosine theta d theta gives us du, right? And then sine theta becomes u. And now here's where things become interesting. Since we're performing a substitution, we need to apply to the endpoints. And this will give us the sine theta, which is 0, and the sine of 3 pi over 2, which is -1. And here you might look at this integral and think to yourselves, oops, is this going, what kind of number is this? Is it positive? Is it negative? And we have to be a little alert about this. I mean, when you compute an integral, right before you do any computation, try to guess if you can tell what the sign would be. And here, if you look at the integrand, it's x times y. If you remember that x is less than 0 and y is less than 0, that tells you that it's a positive integrand. So you should expect this to be positive. In any case, here that should not bother us because we get u squared over 2 from 0 to -1. So this would be really 1/2 minus 0. So that would give us simply 1/2. And when we put everything together, that is going to be 15/8. And that completes our computation. And also the sign of the integral that we found checks out with the prediction that we would have had from the beginning, had we just looked at the sign of the integrand. And I would like us to do now a much more exotic and interesting example. So let's look at one of the most famous integrals in mathematics, the so-called Poisson integral. I think it has other names too, Euler-Poisson, but the bottom line is that it's this integral from -infinity to infinity of e to the -x squared dx. And it's an integral that is linked with the Gaussian distribution, obviously. And we would like to know how much it is. And of course, you look at it and you think to yourselves, why am I even bothering to get into this? This is an integral of one variable. What does it have to do with two variables? It's certainly one of those cases where you cannot find the antiderivative right away. So you have to think in a slightly different way. So here's what we're going to do, actually. We're going to call this integral I. So let's call it I. We don't know what I is, but regardless. So then I squared would be equal to the integral from -infinity to infinity of e to the -x squared dx all squared. And at first, again, it looks like an unexpected trick, but mathematics is full of such unexpected tricks that eventually can even evolve to general methods. And here you would take this integral and multiply it by itself. That's what the square of a number is, right? And here we would do the following very, very innocuous observation that when you look at an integral, the variable of integration is really irrelevant, right? I mean, it doesn't matter whether you call it x or y or z or alpha or beta or anything you like. So it should not be a big concern if we write this the second one actually in terms of y. Yes, but the moment we write it in terms of y, we can really see the kind of product that we get when we split an integral, which means that we think that this now could have come from a double iterated integral that could have simply be this one. We did take a little license by considering these improper integrals, but please bear with me here. And once we do that, then we realize that we have that this double iterated integral could have come up from a double integral over the whole r square of this function. And now the consideration becomes, can we do it in terms of polar coordinates? So in terms of polar coordinates, here's what's happening. So we have r that varies from 0 to infinity, right? These are all the possible values for r, and theta, you just need to go all around from 0 to 2 pi. So that's our first step. The integrand now, on the exponent, you have minus x squared plus y squared, quantity x squared plus y squared, which is r squared. So this will be e to the negative r squared. And then finally, the last step is to insert the Jacobian. And as you can see, this would make all difference in the world. This would even split here. So you would have the integral from 0 to infinity of e to the negative r squared times r dr times the integral from 0 to 2 pi p theta. And of course, the second integral is very, very simple. It's 2 pi. For the first integral, you might want to do a substitution. So u is equal to r squared. Du would be 2r dr, or r dr, which is what we have, is 1/2 du. And this would turn out to be e to the negative u times 1/2 du. And the endpoints, if you plug them into the substitution, is 0 square is 0 and infinity square, well, that should be infinity. You can really integrate this. I don't even have to write it as a limit if we just interpret e to the negative infinity as 0. So this would be negative 1/2 e to the negative u. That would be the antiderivative from 0 to infinity. Again, when I say infinity, it has to be interpreted as the limit of e to the negative b as b tends to infinity, which is 0. And basically, this would be equal to 1/2. So if you multiply the two together, you get 1/2 times 2 pi, and this is simply pi. Well, we're almost done. Let's recall that I squared is what was found to be equal to pi, which means eventually that our celebrated Poisson integral is simply equal to the square root of pi. And that's our computation. This is a very, very impressive result. You start with the exponential function, and all of a sudden, the number pi shows up, something that happens very, very often. So with this, we close our discussion of integration in polar coordinates. Thanks for watching.